Welcome to this session. In this video, we are going to discuss the classification of foliations and lineations, and we mainly will talk about those related to deformation processes. Yet many foliations and lineations are not secondary ones, are not related to deformation processes. They might be primary foliations, and that might include magmatic layering, flow banding in rhyolites or schlierens, as we see them here on the right hand side. These are relics of material in migmatites that has not yet broken down in melt producing reactions. Very often these are diffuse patches of biotite that we can see here in this undetected rock. We also find them in some in situ granites, aligned pebbles in conglomerates or possibly even sedimentary bedding might be classified as foliation, provided that it is planar and regular and uniform in thickness. And that is the definition of any foliation. Foliations are planar features and they show more or less regular spacing and more or less uniform thickness between the individual packages of foliated rocks. There are four common types of secondary foliations, and secondary structures are those that are related to deformation processes in rocks. Cleavage and schistosity and the subtypes associated with them are the most commonly known and probably most important forms of secondary foliation. Differentiated metamorphic layering is also very common, particularly in medium to high grade metamorphic rocks. And then there's myelonitic foliation, which occurs in high strain zones of rocks. We see here examples of foliation types here, a cut block that beautifully shows the intersection of the foliation surface with these two sides of the block. At the top, we would be looking onto the foliation. Here in this sample, we see small scale folds that overprint the foliation that has formed. There is some kind of segregation into differently composed layers. We are coming back to that a little bit later. And here we see a myelonitic zone in a metaconglomerate. Clearly here the strain gradient is increasing upwards here into this about ½ meter wide high strain zone, where we see a very strong stretching and flattening out of the former pebbles in this metaconglomerate. At the top of this block here, we see strain is decreasing again. This would be a myelonitic zone in this metaconglomerate. The origin of tectonic foliations follows a number of different processes. Since we see a large variety of foliation types, we also can assume that there are a number of processes that can lead to the formation of foliations. All of them have to do either with the rotation of strain markers or the deformation of strain markers and their alignment into one preferred orientation. This diagram lists the most important ways in which foliations can form, and they come from Paschi and Chow's beautiful textbook. Let's discuss them one by one. Here we see two examples of more or less randomly oriented markers. These could be fairly small scale markers with a random orientation in a rock. They also could be larger prismatic crystals, for instance, feldspar phenocrysts in a granite. And when such rocks undergo shortening, indicated by the arrows here, we will see that during the shortening, the lateral shortening, our strain markers will respond. And this can happen in different ways. We see here a lot depends on the orientation of the strain marker with the shortening direction. For instance, the horizontal strain marker that we see here undergoes shortening perpendicular to the layering, to the foliation that is forming by the other markers which are rotating into a vertical position here, into one preferred orientation, and they may even undergo stretching. We see here the length of the vertical marker here has increased during lateral shortening. Lateral shortening and vertical stretching goes together with the rotation of markers with their either stretching or shortening processes, which depend on the orientation of the marker, with shortening and stretching directions that is controlling the formation of the foliation. Also, the larger markers that we see here, they are responding in a similar way. We see those which are oblique to the shortening direction rotate towards the stretching direction, and markers that are already oriented in that orientation might not respond at all. They might just stay where they are. Markers that are parallel to the shortening direction might undergo kinking or folding or fracturing because they are at a high angle, and if they are very brittle under the conditions of deformation, they might break or fold. In examples 2 and 3, we see markers that are touching each other, and they are responding in a different fashion. When we look at example 2 here, we can see that dissolution creep is taking place. We change the shape of our originally spherical strain markers, and we form ellipsoids, and we can see that here in the strain shadow a new material is precipitated. This could happen by dissolution creep. It also could happen by grain boundary diffusion creep in order to stretch the mineral grains parallel to the stretching direction and shortening them parallel to the shortening direction. Example 3 here shows a similar situation at the beginning, but here we apparently are deforming minerals that are more plastic, and here we see a coherent stretching and shortening of these mineral grains, most likely controlled by dislocation creep or strongly diffusion-dependent deformation mechanisms. Example 4 is a kind of variation of the two previous examples. We see here a rock that consists of a variety of mineral species, and we can see that some of these mineral species are prone to dissolution. This changes the configuration and the relative abundance of mineral phases, because those which are dissolved will decrease in abundance once the fluid phase is extracted, and we can see that the less dissolvable mineral species are rotating into an orientation parallel to the developing foliation. If that happens at large scale, initially randomly oriented or obliquely oriented strain markers will align with the developing foliation. We have discussed this process in the context of dissolution creep in a previous section of the course, and you can look up the video on deformation mechanisms and dissolution creep for more information. Example 5 shows here randomly oriented strain markers as we would find them in undeformed granites, and lateral shortening again will allow some of the markers to rotate into what will become the foliation. Other strain markers might undergo dissolution, others undergo thickening or lengthening depending on their orientation with the shortening and stretching directions during plastic deformation. If foliations develop during prograde metamorphism and new minerals are starting to grow, which almost always requires the presence of a fluid phase, we might start with small crystals which during deformation will grow in an orientation that is favorable to the strain field, to the shortening and stretching direction. And if that happens at large scale, we will find the growth of minerals in uniform directions, and that will define a foliation plane. Pre-existing foliations might be enhanced due to the nucleation of new minerals. Most commonly you might find in mica schists that contain essentially white mica, muscovite, the nucleation of biotite on the pre-existing crystals, and of course the new arrival of a new phase, in this case biotite, will contribute to the metamorphism of the rock. The last example here has something to do with recrystallization and grain coarsening. We see here a pre-existing foliation, and in between mica grains, sheet silicates, typically you see a granoblastic pattern of other minerals, which for instance could be quartz, and during heating and static recrystallization, grain boundaries can become mobile and might eliminate, and some of them might get eliminated, which would leave behind larger crystals, and the shape of these larger crystals would be elongate, predetermined by the orientation of the mica. So we see here a granoblastic pattern is replaced by elongate, larger but fewer grains in between the mineral that is defining the foliation. Overall, this will macroscopically lead to a visibly enhanced foliation. In order to classify different types of foliations, a number of criteria can be used, and here they are listed. These 4 criteria allow a very simple classification system according to Paschier and Chow. The criteria that we are using is the spacing of cleavage domains, the grain size, the presence or absence of microlithons, and the presence or absence of crenulations. So now we are introducing here a number of new technical terms. What do they mean? Cleavage domains are parts of the rock that are strongly foliated. These are typically layers. They are parallel to each other, and these cleavage domains show a high abundance of aligned sheet silicates. Most commonly that would be micas. If you think, for instance, about mica schists or gneisses, they very commonly have these layers in which the mica is concentrated. These would be the cleavage domains. The microlithons are the parts of such rocks which are separating the cleavage domains. Commonly in microlithons you will find light-colored minerals such as quartz and feldspar. Crenulations are folded microlithon and cleavage domain interlayers, and these crenulations are small-scale features. We are talking about millimeter-sized, small-scale folds in such foliated and layered rocks. Here we see Paschier and Chow's classification schemes in kind of a flow diagram. The application of this diagram is fairly straightforward. The first question you would ask when you assess the foliated rock is, are microlithons present? If that is not the case, you are looking at some sort of continuous foliation, a foliation that is not separated by unfoliated layers. If microlithons are present, then you would talk about spaced foliations. Now, continuous and spaced foliations can be further subdivided depending on the grain size and depending on the presence or absence of crenulations. Let's have a look at the continuous foliation first. if you are considering a fine-grained rock, such as a slate or shale, or perhaps a phyllite, the foliation would be very small scale, very narrow, and you would probably struggle to distinguish individual mineral grains with the naked eye. Such foliations are continuous cleavages, sometimes also called slaty cleavage. Although, to my perception, the term slaty cleavage has become a little bit outdated. Continuous cleavage is probably the better term for this type of foliation. In coarser grained rocks, that means microschists perhaps, where you easily can recognize the individual mineral grains, such a continuous foliation would be referred to as continuous schistosity. So the difference between continuous cleavage and continuous schistosity is simply the grain size of the rock in which the foliation is developed. In spaced foliations, the distinction between spaced cleavage and spaced schistosity follows the same rule. Spaced foliations in fine-grained rocks will be referred to as spaced cleavage. If the rocks are coarser grained, so we are talking about half millimeter or millimeter size and beyond, the spaced foliation would be a spaced schistosity. And here we see in the diagram how we distinguished cleavage domains and microlithons. Here in dark color with partly some anastomosing patterns, we see cleavage domains. These layers would be full with sheet silicates, where the sheets are parallel to these layer boundaries. And in between we would find the microlithons with coarser grained, usually light colored quartz or feldspar minerals. Now, if we have a spaced foliation, and particularly in finer grained rocks, we sometimes find crenulations in the microlithons. Here on the right-hand side, this is schematically shown how it would look like. We see here cleavage domains running from top to bottom, and in between in the microlithons, we see the relic hinges of small-scale folds. We are going to explain how these features are forming, but for the purpose of the classification, for now we are only interested in whether these crenulations are present or whether they are absent. If they are present, we refer to this form of spaced foliation as crenulation cleavage. If they are not present, we simply would talk about a spaced cleavage, sometimes also as disjunctive foliation or disjunctive cleavage. Practically, there is no difference between a disjunctive foliation and simply a spaced cleavage. There are no differences in the texture and structure that we observe. It is a bit unfortunate that the literature on structural geology does not agree on one single classification scheme, and if you read other textbooks, for instance Davis and Reynolds' textbook, the definitions are slightly different, and what is referred here as a spaced foliation is more or less a disjunctive foliation, and disjunctive is referred to as spaced. If you want to avoid unclarity in the texts that you write about your observations, the best way is to refer to the specific classification system that you use, or simply describe what you see. A good petrographic description would not simply say that the rock contains a continuous foliation. It would also provide reasoning why and how you identify this type of foliation. So simply report the observation that you make in the field. Here we see some examples. On the left-hand side, this is a phyllite. You can see the silky, shiny surface. A metaphylitic protolith can be assumed in this case. And we see a very strong foliation that is developed throughout the rock, and there is no separation in more or less intensely foliated parts of the rock. So here we cannot separate cleavage domains from microlithons. The whole rock is just a very large, big cleavage domain. This would be typical for a continuous cleavage. That's what they look like in the field. Here on the right-hand side, we see a clear separation into lighter colored layers, which are quartz feldspar-rich and mica-rich layers, biotite-rich layers. These biotite-rich layers would be the cleavage domains. The microlithons in between are quartz feldspar dominated. And we can see that the interlayering of microlithons and cleavage domains has undergone some minor folding. You would not refer to this kind of folding as a granulation because it is simply a little bit too large scale for granulations. We are going to look at granulations in a moment. In thin section, continuous cleavages might look like this. This is taken from Bashir and Charles' textbook, which shows a number of very good examples of foliation types. The main characteristic of continuous cleavage is that we are looking at fine-grained rocks. The width of view in this image here is 1.8 millimeter. That means the grain size is way below what you could see macroscopically with the naked eye or even with a hand lens. And we cannot see here a clear separation of quartz-rich and mica-rich layers. It looks pretty much uniform, particularly here in this part that is very uniform. Here we might regard some sort of minor separation, but overall continuous cleavage is an appropriate classification for this example. Here we see clearly a spaced, or if you want, disjunctive cleavage. Clearly here we have thin cleavage domains that are mica dominated, separated by microlithons that are a little bit more quartz rich. There's also some mica in the microlithons, but overall there is a good separation between light colored and dark colored layers. If you would take such a sample and try to split it, it would always split along the cleavage domains. Let's find out how granulations and granulation cleavage is forming, and the process that leads to the formation of these structures is called the transposition of foliations. Transposition means simply an overprint of an existing foliation that leads to the formation of a new foliation and might even obscure earlier foliations so that they are no longer recognizable. This process is commonly associated with folding, and it is most typically seen in mica-rich rocks. Folding requires some form of lateral shortening, and this typically forms an axial plane cleavage. Complete destruction of the first foliation might occur. So here we see how granulations and granulation cleavages develop during progressive shortening of an existing layering that consists of an earlier foliation with microlithons and cleavage domains that are intercalated. In the first stage, we see here that open microfolding is taking place, and again, this is a feature that would be observable at probably thin section scale. So here we see these open folds, but we see still a very good separation of the first generation cleavage domains and microlithons. With increasing lateral shortening, we see that the amplitude of our microfolds is increasing, and we can see that along the limbs, the softer layers, the less competent layers, which would be the cleavage domains, start to thin out and they start to lose all quartz and easily dissolvable material due to dissolution creep. In the hinges, we see increasing thickening of these less competent layers due to ductile flow of material, and the absence of dissolution creep. As soon as we shorten even further, we will find that the thinner layers, the first generation cleavage domains, are starting to thin out to an extent that the coalescence of micas along the limbs of the microfolds starts to take place. And here we can see that a new foliation is forming. That would be the second foliation generation, normally referred to S2. In between the S2 foliations, we see that a new microlithon has formed, and this microlithon contains relics of the former layering of the earlier microlithons and cleavage domains that are still visible here as relic hinges of these crenulations of the microfolds. And as soon as this stage is reached, that we have a through-going interconnected second generation foliation, we would talk about a crenulation cleavage. The crenulations are present as relic structures in the newly formed second generation of microlithons. Here we see an example in a thin section. We find here these bent and crenulated first generation layers. So the micas here would be part of the S1 of the first generation cleavage domain. In between we see more quartz-rich domains. That would be the first generation microlithons. We see that also here quite clearly. Some static recrystallization has taken place, and we see here fairly straight micas that have recovered, but they are following this crenulation, this microfolding. Along the limbs of these microfolds, we see that a new crenulation cleavage has formed, and mica-rich domains have coalesced and form this new cleavage that we also would see over here and here. So again, the crenulation is the microfolding, which we find in the newly formed second generation microlithons. That would be this area here, as relics of the first generation layering with first generation S1 planes and the microlithons in between. The crenulation cleavage are the newly formed S2 foliations. Another example from Pashier and Zhao's textbook, very prominently developed S2 foliations up here and here, less prominent in between, but yes, there is a very clear second generation foliation developed. And in between, in the microlithons, we still see a lot of light-colored material, quartz-rich relics of the first generation layering with crenulations. In microlithons, we see here clearly relic hinges of these crenulated S1 foliations. In this series of images, we see progressive overprint of an earlier foliation. Here on the left-hand side, we see plenty of crenulations with crenulation cleavages cutting across them, but the original first generation, the S1 foliation, as crenulated relics with interlayered with their microlithons, is still abundantly visible and straightforward to recognize. In more intensely sheared parts of the same exposure, we see that the domains in which the overprint is prominent are growing in thickness, and still in some parts we see the S1 crenulation that belonged to the first deformation event. And here in the third part, we see that these relics of the S1 and the crenulation are largely obliterated. Here we see a dominant second generation foliation with newly formed microlithons, and newly formed cleavage domains. So in this area here, if you only have access to this part of the outcrop, it would be quite difficult to identify the earlier stage deformation, the D1 deformation, which we would see prominently here preserved in the relic microlithons and the granulations of the first generation of the D1 event. The transposition of folds is the large-scale equivalent of the transposition of foliations that we have just discussed, and which leads to the formation of granulations and granulation cleavages. At larger scale, a similar process takes place in rocks that are layered and where different layers have different competence. That means different rheological characteristics, and more competent layers and less competent layers form these sequences of rocks. Here we can see how folds develop and how they, with increasing lateral shortening, become tighter and tighter, and the amplitude increases. We can see here that this lateral shortening converts the rock into a pattern where we see lenses of more competent layers interbedded with less competent matrix material. And the transitional type is a process that involves the thinning out of limbs. We see here the more competent layers, the black layers, show a strong thinning of limbs and a fairly intense thickening of the hinges, which eventually leads to the disruption of limbs. And here we see this transitional stage. We see these hook-like relics of the hinge zones, but this hinge here has separated from that hinge because the initially connecting limb is disrupted, is sheared off. And in this stage, we still can identify that this rock clearly has formed from an interlayered rock that once was intensely folded. In this stage, the indicative features, these little hook-like shapes of the hinges of former folds, have been removed by dissolution creep, and all that is left over are these lenses of competent material in incompetent matrix. Again, if you map out areas and you come across rocks like that, it would not be easy to identify from the evidence that you see here that this rock initially was a interlayered rock that underwent intense folding and underwent the transposition of these folds. For the field geologist, such evidence would require that you look for less deformed parts in the same rock sequence, and you might find relic hinges that give away that you are not looking at rocks with lenses, you are looking at rocks with sheared off hinges of folds that initially goes back to an interlayering of competent and less competent layers. The disruption along these hinges is a process that we refer to as boudinage. And boudinage always affects the more competent layers in an interlayering of rocks with different rheology. So the checking for relic hinges when you work with rocks of different competence that are showing this kind of lens-shaped patterns is a recommended step in order to perhaps identify transposition of folds as a process that has led to the formation of these lens-matrix relationships. Here we see an example of such a situation. Here these white layers would have been the more competent ones. Probably these are quartz feldspar dominated lenses in a more micaceous, softer matrix. And we can see here these typical lens shapes that grade into layers that we see here. All these are very likely limbs of folds that got disrupted and now form isolated lenses in the softer matrix. The last type of foliation that we need to discuss is myelonitic foliations that are commonly seen in ductile shear zones. The definition or requirements for myelonitic foliations is a significant grain size reduction due to plastic deformation. Many geologists would associate myelonites exclusively with plastic deformation, but the grain size reduction can also take place in the brittle field. And this is the criterion. Plastic deformation is most common to form myelonite zones, but it is strictly speaking not a requirement. What is a requirement is that in a myelonite zone we see a significant increase of strain compared to the material that hosts the myelonite zone. That means if we are looking at terrain that has penetrative foliation that is developed everywhere, even if this foliation is intense, you would not refer to it as a myelonite. A myelonite requires a localized increase in deformation intensity compared to the host rocks. What you also would want to see, and what is most common in ductile, in plastic myelonites, is the recrystallization of porphyroclasts. That means crystals of initially larger size that show the grain size reduction and perhaps even their obliteration in proto and in ultramyelonites. That means in myelonites that show very intense deformation. Myelonite zones also may cross-cut earlier foliations. Very typically, myelonites form during younger deformation events. So if you are in a gneissic terrain that already was deformed before the myelonite formed, the myelonite might have a different orientation compared to the foliation in the host rock. If that happens, the earlier foliation might be dragged into the new myelonite shear zone, and under ideal circumstances you can use that as a shear sense indicator. So here we see myelonite zones cross-cutting a granitic protolith that is much less deformed. Here on the left-hand side we still see some foliation, but the rock is clearly much coarser grained and shows much more relics of the magmatic stage. These are very likely alkali feldspar porphyroclasts that initially were phenocrysts. On the right-hand side, there is an almost intact granitoid protolith, probably a tonalitic rock, cross-cut by a myelonite zone, and we can clearly see the deformation intensity increasing in the myelonite zone compared to the less or undeformed protolith. This is what a myelonite should look like, a sudden increase in deformation intensity. What we can see in both images is the intense grain size reduction in the myelonite zones, also the intense alignment of strain markers as long as they are present. In the ultramyelonitic part, the foliation becomes not very prominent because the grain sizes are so small and elongate strain markers are absent here. Here we still see them, but in the myelonite, in the ultramyelonite, all strain markers, all porphyroclasts have been recrystallized with such an intensity that they are no longer visible with the naked eye. Here on the right-hand side, we see throughout the myelonite zone a continuous foliation. We see in some parts relics of the protolith that are less recrystallized, but overall also here we see an intense deformation, and we can see here a foliation is dragged into the myelonite zone. So Along the margins of the myelinite zone, some deformation has affected the protolith, produced some foliation that is dragged into the orientation of the myelinite zone. The process of a strain concentration in such myelinites is referred to as strain partitioning. That simply means that some parts of the rocks have experienced very intense deformation and strain, whereas nearby other parts are much less deformed or perhaps even undeformed. Here we see a microscopic image that shows similar features, a weakly deformed granitic protolith with large feldspars. Darker materials are probably oxides and probably biotite. And here we see some foliation, some evidence of deformation, but and here an offset feldspar clasts. But overall, the deformation intensity is much lower compared to the proto-myelinite, which shows a spaced foliations with some sort of microlithons and separated from cleavage domains, not very well developed, but at least in some places that is visible. And we see a myelonitic foliation here at the bottom end of the image. Here a clear separation into light colored layers and into more foliated cleavage domains. So cleavage domains and microlithons are here reasonably well separated. In the high strain zone of the ultramyelinite, this separation is no longer visible. We see a very intense foliation, but grain size reduction has eliminated almost all porphyroclasts. Only very tiny little specks of the former feldspars are still visible. The rock that we see here is in its composition and textures dramatically different from the protolith from which it has formed. The difference between a myelinite and an ultramyelinite is gradual and qualitative. There is no sharp boundary where you could say this is definitely an ultramyelinite and this is a myelinite. We see here kind of a comparison. In a myelinite, you should still see abundant porphyroclasts. You see here sigma clasts and other shear sense indicators. You see the deflection of foliations around these harder porphyroclasts. But overall, you see intense deformation, and you should see nearby much less intensely deformed protoliths. In an ultramyelinite, even in thin section scale, you should see that most or almost all porphyroclasts are eliminated. Here are still some visible, but in proper ultramyelinites, they all should be gone. They should be recrystallized and have undergone dynamic recrystallization and dissolution creep, which destroyed porphyroclasts. Let's come to linear fabric elements. Again, in lineations, we also have primary ones. These are features, linear features that have formed before the lithification of the rock. And these could be, for instance, the crests of ripples in sandstones. They also could be the ropey shape of pahoehoe lava that forms before the solidification of the lava, or it could be the alignment of crystals during magmatic flow. If you have long prismatic feldspars or amphiboles in a magmatic rock and they get aligned during magmatic flow, they could present a lineation that you will be able to identify after the solidification of these rocks. In structural geology, we are more interested in secondary lineations, and they are the result of deformation. A very common type of lineation is the intersection lineation. Two intersecting planar structures show traces of each other on the surfaces. So joints, for instance, will show the trace of a foliation that on this surface, on this joint surface, it looks like a linear structure, but it is actually only the intersection trace of another planar surface. Bedding also would form a trace on a cleavage plane or on a joint, or two intersecting cleavages might form intersection lineations. So intersection lineations are simply the trace of one planar structure on another non-parallel oriented one. We have talked about granulations, small-scale folds, and these granulations will have hinge lines. The crests of these hinges, the crests and the troughs of such granulated cleavages could form a lineation that is also parallel to the fold axis of these small-scale folds. And then there are mineral lineations, alignment of prismatic or fiber-like minerals, typically it would be amphibole or sillimanite, which have grown in a preferred orientation and then are a linear fabric element. For structural interpretations, the most important lineation are stretching lineations. Stretching lineations reveal the direction of tectonic transport, and they are formed by the stretching of strain markers by crystal plastic deformation. Fiber lines are transitional between mineral and stretching lineations. So fiber lines we typically find along brittle falls where fluid was present and precipitated minerals, most commonly quartz, in a fibrous linear shape, which is not the normal shape how quartz should crystallize. But during tectonic displacement, minerals can grow in the direction of tectonic transport. So fiber lines would be transitional between a mineral lineation and stretching lineation. They form during stretching, during a displacement process, but they are not consisting of a deformed mineral because the mineral that forms the fiber lines actually grows in this fibrous shape and may well be undeformed. It is important that for kinematic interpretations and for the determination of the tectonic transport direction, only stretching lineations and fiber lines should be used. Of course, you also can use striations on brittle faults, which also are secondary lineations, and but we are not discussing them here. We have discussed them in a different section of the course, and you can look up information on striations and stick-in sites in a different video. Here we see a summary of such lineations. Up here, this would most likely be a mineral lineation, perhaps tourmaline or amphibole, that are aligned and may have grown in that orientation. Minerals that form a mineral lineation do not show evidence of deformation, of particularly plastic deformation. So all we see here is a preferred alignment of undeformed crystals. Here we see an example that shows lens shape, strain markers aligned along a foliation. This probably would be some form of LS tectonite. The lens shape shows one preferred stretching lineation. We would find something like that, for instance, in sheared granites where former phenocrysts, K-feldspar phenocrysts, show a flattening and a stretching in one preferred direction. A similar feature is seen here, only that the lenses do not show a preferred orientation with their intermediate axis, but the longest axis is still well aligned with a uniform linear orientation. Intersection lineations are shown down here. Simply the intersection of one surface on the other. For instance, the foliation that we see here is visible as a trace on the front of this block, which could be a joint, for instance. And the granulations that we have discussed before, there may or may not be a granulation cleavage developed. Here it is actually not quite clear that a second foliation has formed and that a granulation cleavage is present, but clearly we see the microfolding, the granulation, and the crests and troughs of the microfolds define a clear linear fabric. I also want to come back to the L-tectonites, which are rocks that have formed during constrictional strain or prolate strain, where we see pencil gneisses, for instance. A strong lineation is developed throughout, but a foliation is largely absent. Here in the photograph, we see a LS tectonite. We see foliations are developed, and on the foliations, we see a very clearly developed stretching lineation of quartz and probably also feldspar. This would be a high temperature shear zone, perhaps myelonitic, perhaps not. We don't see the context, but clearly a lineation, a transport lineation is clearly visible on a foliation that is steeply dipping towards us. In the essence, that is all I have to say about foliations and lineations. Thank you very much.